introduction for him. He got the PhD at Boston University under the supervision by Claudia Schamann. And then from then, he worked on from the graduate school, he worked on the quantum computers and the non-equilibrium systems. And these days, he moved to the University of Maryland, JQI, Joint Quantum Institute. And then he has been quite prolific for the several couple of years. And then he has been known for his works on the non-equilibrium systems and the quantum computations and the strongly correlated systems. And today, I think he's going to introduce a new way of constructing the quantum spin liquid in the name of the combinatorial gauge symmetry. So Ji-Chang, I think you can start.
Okay. All right. Thank you for the nice introduction and thanks for the invitation. So if you have any questions, just feel free to interrupt because, with the Zoom, it's kind of sometimes it's hard to keep track of the audience because I don't see anyone directly. All right. So, I mean, as far as I remember, it's probably my first time ever giving a talk in the evening, in local time. So it's yeah, it's kind of interesting. Okay. So today I'm going to talk about this recent work that we did on constructing quantum spin liquids using combinatorial gauge symmetry. This is our paper. If you're interested in more detail. So for this particular work that I'm going to be talking about, this was done in collaboration with Dimitri Green and Claudio Schamann at Boston University. However, at the meantime, we've been working on various generalizations of this idea. And for example, we're also working on some quantum Monte Carlo studies of this model that we proposed. And that part was mostly done with or by Kai-Xin Wu as a graduate student at BU, and also Anders Sandvik. And also we've been working on generalizing this combinatorial gauge symmetry to other gauge groups. And that part is also done with Elliot Yu, who's also a graduate student at Boston University. Okay. Okay. All right, let me start by giving you a brief overview of our main results, basically just a summary of what we did. So basically the goal or what we ended up achieving is that we construct a Z2 lattice gauge theory with only two-body interactions. And the key notion that allows for such a construction is known what we call is actually combinatorial gauge symmetry. And yeah, I just want to emphasize here that this is an exact local Z2 gauge symmetry of the Hamiltonian. And we construct explicit lattice Hamiltonian in 2D where the couplings actually has this combinatorial gauge symmetry so that we have a gauge theory. And then the couplings that having this kind of combinatorial gauge symmetry, it turns out to take the form of Hadamard matrices. And we also generalize our constructions to other gauge theories, for example, 3D toric code, and also the X-cube model, which is known for the fractonic topological order. And eventually, I will briefly mention this is a recent progress of a superconducting circuit realization of this combinatorial Z2 gauge, combinatorial gauge symmetry for Z2 gauge theory. Okay, so quantum spin liquids. Just a brief introduction. This quantum spin liquids have been, developed for decades, and then back in the days, it was introduced by Wegner in 1971 in the context of Z2 lattice gauge theory. And it was also considered by Phil Anderson in 1973, where he proposed his famous resonating valence bond state as the ground state of certain frustrated anti-ferromagnet on the triangular lattice. And later in the 1980s, it was revisited in the context of a high temperature superconductivity. So at first glance, an approximate definition of quantum spin liquids is basically that it is a quantum paramagnet that does not break any symmetry of the underlying Hamiltonian. So really it's phenomenological description that the system does not order even down to zero temperature. And of course, after theoretical efforts for many years, right now we've started to look at quantum spin liquids from completely different perspectives. And in particular, it led to this notion of topologically ordered phases of matter. And the system does not have long-range order. And importantly, the system has this local gauge symmetry, whether it's intrinsic or it's emergent. And also the system has fractionalized excitations. So you can see that on the theory side of quantum spin liquid, it is extremely rich. However, concrete physical realizations, in particular in terms of real world materials, so far has remained debated. So I want to give a concrete example of quantum spin liquid, which it's an exactly solvable model. It's known as the Torrey-Colt model. I think what I'm going to say about this Torrey-Colt model, I believe is really well known to the audience, but let me still, just to be complete and also set the stage in terms of notations and everything, let me just mention a few words about this as well. So consider a square lattice. Of course, you can define Torrey-Colt on, for example, honeycomb lattice as well, but we consider square lattice. We put spin degrees of freedom on the links of the square lattice. And there are two types of operators in the Hamiltonian. The A operator, usually called the star operator, it's associated with the vertices of the Hamiltonian. So basically, you take the product of the four sigma z's on the four links emanating from a star. And then the second operator is the B operator, or the plaquette operator. Basically, you take the product of four sigma axes around an elementary plaquette. And then the Hamiltonian is basically a sum of the all the stars in the plaquette terms. And notice that we're actually, you might have noticed that we're actually using a slightly different convention than the form that you're familiar with, because usually the stars are written in terms of the X and the plaquettes are written in terms of C's, but that's just to be in alignment with the notation that we happen to be adopting in this work. So I mean, that's a slight difference, but it doesn't matter. And one can check that the A's and the B's commute, and also A's and B and B commute apparently. And also the A and B's, they square to the identity, so that the eigenstates of the Hamiltonian can be specified by specifying the values for each of the star and the plaquette operators. And okay. Apparently, you see that the A and the B operators contain four spin interactions. And now, let me try to explain the magic of the four spin interactions. Why these kind of models with exact local gauge symmetry often involves multi-spin interactions. Let's for the moment kill the speed term. So we have a classical Hamiltonian in the Z basis. Now, the ground state, of course, has A equal to 1 for all vertices, right? So in terms of the microscopic spin degrees of freedoms, there are 8 degenerate star ground states that multiply to +1. Now, let me draw this up pointing spins as a blue link and down pointing spins as red link. So here, these are the 8 degenerate star ground, classically degenerate star ground states. This is basically the 8 vertex model. And you can actually check that the number of down pointing spins associated with each vertex has to be even, because then it has to multiply to +1. And on the full lattice, when you put the system on the full lattice and you consider the classical ground state on the lattice, you will see that the down pointing spins have to form loops, because for each vertex there has to be an even number of down pointing spins. And in particular, all such loop configurations are energetically equally good on the lattice. So classically, without this, the plaquette operator, there's a massive degeneracy in the classical ground state of this model. Okay, now let's turn on this this B operator. So what this B operator does is that it flips 4 spins around an elementary plaquette. So for example, I take this plaquette and then apply the B operator. So what it does is that you see that it changes the loop configuration. Basically, it brings you from one loop configuration to the other loop configuration, and you can call this a loop surgery. And as a result, the ground state in the presence of the B term is actually a superposition of all loop configurations on the lattice, and it doesn't break any symmetry. It doesn't order in any way. And in particular, you can check that the ground state is invariant under the B operation for arbitrary plaquette. And then this is basically a manifestation of the local gauge symmetry. So I'm writing in terms of the Charry-Colt model, but in a slightly different, well, it's actually related. And the Z2 gauge theory is slightly different, but actually it's not that different. So the Hamiltonian for the Z2 gauge symmetry is that instead of having both the A and the B operators, you only have the A operator here. And then you have a transverse field along the X direction. So basically, as you increase the transverse field, it's going to drive a phase transition from the Z2 topologically ordered state to a trivial paramagnet. But even though you don't put the B term in this Hamiltonian, the Hamiltonian still has this local gauge symmetry generated by the B term, so that you have to put this gauge constraint that B of P is equal to 1 for every plaquette. And the difference in the Charry-Colt model is that instead of imposing this hard constraint, you soften the constraint by putting that term in the Hamiltonian with an associate energy scale, so that the ground state has to be satisfy the gauge constraint. And apparently, this you can see that even if you don't put the gauge constraint, when you do perturbation in gamma over lambda, the lowest order term that you generate that brings you that act within the ground state manifold of A of V is precisely this term, is that you flip around the plaquette and brings you back. So it's really not that different. It's just Charry-Colt is exactly solvable. Okay, now let me say something about really about the magic of the force-spin interaction. Again, this is well known, but hopefully let me try to explain that from sort of a different perspective. Now you can see that in the absence of any quantum mechanics fluctuation, like in the Z basis, you get these 8 vertex configurations that are equally good energetically. Okay, now you turn on the quantum fluctuations. Now, usually when you start with this from a system that contains a massively degenerate classical ground state, usually at the moment you turn on quantum fluctuations, the quantum fluctuations will typically, what it will do is that it will energetically favor a subset of classical configurations as the true ground state in the presence of quantum fluctuations, as the ground state of the entire Hamiltonian. And in other words, by selecting the subset of configurations is basically forming some sort of ordering pattern on the full lattice. And then this is the usual scenario. This is known as order by disorder. And this is why, when people look for quantum spin liquid, they look for frustrated lattices with the massive classical ground state degeneracy. But why quantum spin liquid is really hard is that when the moment you turn on quantum mechanics, instead of getting a quantum spin liquid, usually what you're getting is order by disorder. It's really easy for quantum fluctuations to actually selecting certain ordering pattern on the lattice. So you can see that the magic of the force-spin interaction in the Charry-Colt or the Z2 gauge theory is really not that it gives you this the 8 classically degenerate ground state. Its essence is really that it gives you this local gauge symmetry that evades order by disorder. So instead of order by disorder, it generates this massive superposition in the ground state without any ordering pattern. So when you try to engineer write down any Hamiltonian with fewer body interactions, and this is the thing that you really need to keep. Okay. And then, of course, when you put the Charry-Colt model on the torus, it turns out that the A's and B's are not all linearly dependent, and that there's a fourfold ground state degeneracy. And then you can construct these sort of loop operators on non-contractible loops that toggle between the ground states, different ground states. Okay. And now let's ask a question. Is it possible to construct local two-spin Hamiltonians with an exact Z2 gauge symmetry? So the question we're asking here is really different from usually what people do is that they write down a two-body interaction, a spin Hamiltonian with two-body interactions, and then they explore via numerical methods that whether somewhere in the phase space the system is actually a spin liquid. So here we're not asking that. So we are trying to construct a Hamiltonian with a built-in exact Z2 gauge symmetry to begin with. And of course, the answer here is yes. And the key here is combinatorial gauge symmetry. So basically, in a nutshell, what this word means is it is a local transformation that includes single spin rotations as well as permutations of spins, and hence the name combinatorial here. Okay. Now, because essentially we want some sort of transformations on the spins, on the spin degrees of freedom on the lattice, such that it functions as a local Z2 gauge symmetry. But of course, most importantly, we want to do some transformations that preserve the spin, algebra. So we start by asking a simpler question. Now, suppose I have n spin 1/2 degrees of freedom, meaning that I have 3n Pauli operators sigma I alpha, with the alpha denotes x, y, and z. So which transformation preserve this all spin commutation, anti-commutation relations? I mean, this is probably an old problem that you remember back in the days. Of course, for bosons and fermions, we know that the answer, you can just do a Bogoliubov transformation, that it's a unitary transformation on the creation annihilation operators that preserve the algebra. But the spin algebra is kind of bizarre in the sense that different spin degrees of freedom can commute with one another. But whereas the different components of the same spins anti-commute with one another. So immediately you can see that a Bogoliubov type transformations do not work in this case. And of course, you can, for n spin 1/2 degrees of freedoms, the Hilbert space is 2 to the n. You can say, well, I can just do an SU 2 to the n spin rotations on this spin degrees of freedoms. And of course, that will preserve the algebra among the generators. That's true. But the thing is that usually when you do that, you will turn a single spin operator into a product of spin operators. And this is something we don't want on the lattice. And a trivial solution is, of course, I can just do single spin rotations independently on each spin degrees of freedoms. However, here we actually, after a less trivial solution, is that we do single spin rotations plus permutation. Let me just give an example in terms of 4 spins. So consider 4 spins, sigma 1, 2, 3, and 4, and then the vector denotes the x, y, and z components. So you see that I consider this type of transformation because single spin rotation, it acts as the Pauli spins transforms as vectors under single spin SU2 rotations. So here the GIs are elements of SO3. So you can see that this matrix is basically a single spin rotation. And then you can see that this matrix is off diagonal. So it also permutes the spins. And of course, this preserves the spin commuting and anti-commutation and commutation relations. And this matrix, it actually has a name. It's known as monomial matrix, and which is basically some sort of generalization of permutation, because for permutations, all these G's are basically 1. So here, and indeed monomial matrix, you can view this as a semi-direct product of this diagonal matrix G1, G2, G3, and G4, and the permutation group. Okay. And now, since we know that, okay, one class of transformation.
I have a question, sorry. In the previous slide, so when you say monomial matrix, is it the matrix for the 4x4 matrix, or is it the 4x4 times some SU2?
It's a 4x4 matrix.
Okay, I see.
Yeah, so okay. Basically, yeah. So you should really view this as, some SU2 spin rotation. It's like the representation of the SU2 rotation on the spins. Right. Yeah, so monomial basically means that there is only one element per row, one non-zero element per row and per column in this case.
Okay, good. Yeah.
Yeah. Right.
Yeah, thanks.
No problem.
Excuse me, can I ask one question?
Sure.
So, yeah, so is this an element of S4, or what is it an element of? Like, which permutation group is this?
This is not just an S4. It's permutation. It's actually, S4 would just be the permutation, right? So suppose I replace 1, 2, 3, and G1, G2, G3, and G4 just by identities, and then this would be a permutation matrix, and this is an element of S4. But actually, it's basically when you permute, and then you also do single spin rotations. So it's really, the group is not just the permutation. It's basically a semi-direct product of the diagonal 1, 2, 3, and 4 semi-direct product of permutation.
Okay, I want to ask. So it is actually, it's very similar to the formalism by Van Ness. Like several years ago, there were these papers where he constructs two-body Hamiltonians with these monomial matrices. Is it similar? Is it related, your work?
I'm not familiar. So what was the context there?
No, even they are constructing like topologically ordered models with monomial matrices.
I'm not
Okay,
familiar.
it's okay.
Yeah.
Anyway, thanks.
Yeah, but maybe by the time that I'm done with the talk, and then you can let me know whether it's what's the similarity and what's the difference, because
Well, I'm not sure if I can fully understand, but anyway, thanks.
I don't remember off the top of my head at the moment. Yeah.
Okay, thanks.
Okay. Now with the monomial matrix, actually, we can go on and talk about this combinatorial gauge symmetry. Okay. So our construction is the following. So on the lattice, we put this spin degrees of freedom on the links, which we call the gauge spins. That here we denote the gauge spins by the green dots, and we call them sigmas. And on each lattice, we put 4 auxiliary degrees of freedom, which we call matter spins. Here it's denoted as blue dots, and I label them as mu. So this is my convention. So I always label the gauge spins as a sigma and the matter spins as mu. Okay, so now, so this is how it looks like on the lattice. And this is if I pull out a single star. So you can actually see that there are 4 matter spins on each lattice site, and there are 4 gauge spins per star operator. And now in constructing the Hamiltonian for the stars, we consider 2 spin couplings between the that takes the following form. So notice that we're only allowing couplings between the sigma and the mu spins. So here basically I can write the coupling as a WAI sigma I and mu A, the Z component only. So the W is a matrix, a 4x4 matrix, because we have, for each star, we have 4 gauge spins and 4 matter spins. So it's a 4x4 matrix. Its specific form we will specify later because we need to require a form such that the Hamiltonian has this combinatorial gauge symmetry. But the important thing here is that there is no sigma and mu coupling. And on the lattice, you can see that you can see immediately that these matter spins on different sites, they're completely independent of one another, because it's only coupled to the 4 gauge spins adjacent to the site, but they are not coupled among themselves, nor are they coupled to adjacent sites. Okay, so the full lattice Hamiltonian takes the following form. Let me show it now, and then I will justify this or explain this step by step. So for each star, I have this 2-body coupling, this Ising type of CZ coupling encoded by this matrix within a W matrix with an energy scale. And then I also introduce a transverse suit on the matter spins denoted as gamma. So you can view this term in a square brackets as the analog of a star operator, and then you sum over all stars. And then on top of that, I introduced this transverse suit on the gauge spins as well, which we denote as gamma tilde. Okay, so if you look at the Hamiltonian, you see that we only need 2 types of terms, the ZZ, the Ising ZZ interaction, and a transverse suit term. That's the only terms in the Hamiltonian. Okay, so now we want to impose a gauge symmetry. So similar to the sort of the Z2 gauge theory, let's start by considering a single star. So we want a transformation that leaves the single star Hamiltonian invariant. So single star Hamiltonian, you just think of the terms in the square bracket here. And of course, we want transformations that preserve the spin algebra, and we already know that they are monomial transformations. Okay, so let's consider monomial transformations. And now, since there's only this spin Z component, so instead of the full SO3, basically here the matrix only act on the Z components. So we consider the following monomial transformations on the gauge and matter spin simultaneously. So consider sigma I goes to Rij sigma j, where the R here is a monomial matrix, and then mu goes to sigma, mu z times L. So L and R basically here stands for left and right, just to be intuitive. And also, since we're only considering Z2 transformations, so instead of a general G, remember in the monomial transformation I had here, I have elements of group elements of SO3. So here, the non-zero elements of this R and L matrices, we will take them to be either +1 or -1. So here, -1 means that it's basically, in terms of acting on the sigma z's, it's basically a spin flip. And +1, of course, it leaves that invariant. Okay. And then we want the star term to be invariant under this transformation simultaneously on the gauge and matter spins. Equivalently, because we are actually doing a transformation on the sigma and the mu's, and equivalent, you can view this as some sort of transformation on the W matrix, L inverse WR. So the invariance under the monomial transformation really in this language now translates into the following automorphism on the W matrix, meaning the W matrix has to be invariant under L inverse and R transformation. And it turns out that matrices having such an automorphism, it has a special name, it's called Hadamard matrices. So these are basically matrices whose elements are either plus or -1. And it satisfies this condition, W transpose in W is proportional to the identity. In other words, the row and columns of the W matrices are orthogonal. And in this case, because we only consider, remember, we only consider 4x4 Hamiltonians. So we're actually only consider 4x4 Hadamard matrices. And I mean, the name Hadamard actually, if you're familiar with this terminology from quantum computing, if you consider 2x2 Hadamard matrices, this is nothing but the Hadamard gate. It's a single qubit rotation gate. So here we are actually considering 4x4. And it turns out that 4x4 Hadamard matrix is also unique, and we choose this form. Of course, you can write other forms of 4x4 Hadamard matrices that satisfy these properties, but you can show that they are all equivalent up to row and column operations.
Excuse me.
Mm-hmm.
Yes, I'm sorry to interrupt. So for the 2x2 Hadamard matrices, right? They flip the X and Z Pauli operators, no?
Right, but
so the 4x4 doesn't have some property
here,
like that.
The W matrix does not generate the transformation of the spins. The one that generates this transformation of the spins are the R and the L's. So we're not acting on the spins with the W. So this is different. Yeah. So W is not something acting on the qubit, right? Here.
Okay, but the W is the
his name. Yeah.
Okay. Okay, I see. Okay, thanks.
It will be clear because I will give a concrete example of L and R so that it's no longer abstract. Okay. So I was saying that you can write down other 4x4 Hadamard matrices, but you can show that you can always bring them to this particular form by performing elementary row and column operations in linear algebra. So they're all considered equivalent because they're related by these sort of kind of similarity transformations. Okay. Now what we have done, what we have shown is that okay, we consider Hamiltonian that is invariant under this monomial transformations simultaneously on the gauge and matter spins. And then this in turn put a constraint on the W matrix. And eventually a W matrix that satisfies this constraint is basically the Hadamard matrix. And then we further, if you actually look at this R matrix, because as I said, we're only considering Z2 type of monomials, right? So the non-zero elements are basically just plus or minus ones. And then you immediately recognize that this is reminiscent from what you do in the Z2 gauge theory, because whenever you have a -1, this is nothing but a spin flip, right? So now we put one more constraint on the R matrix. Remember the general monomial matrix, the general monomial matrices, like here, it contains both a single spin operation and also permutation. But here, I want to restrict the R to be diagonal, meaning that I only flip certain spins if I want, but I do not allow permutation. And then the reason is following, because this is how it looks on the lattice, right? So of course, on the single star, I can permute the sigma spins. But on the lattice, those gauge spins are shared between two adjacent vertices. I cannot permute arbitrary because if I permute this, I'm gonna spoil this the other stars as well. So I want to keep the gauge spins as they were on the lattice. So I constrain the R matrix to be diagonal, meaning that I only allow spin flips, but I don't allow permutation. But the L monomial matrices, they act on the matter spins that I can permute, I can flip, because permutation, because that's precisely for the reason that that the matter spins are not coupled between adjacent sites, so they're really independent of one another. So here, of course, I can choose to label in whichever way I want. You know, which one is 1, which one is 2, which one is 3. I can relabel them. So permutation is allowed, and also. Here, I've been talking about you know, this -1 spin flips. The spin flip, because in the Hamiltonian, I have a transverse field on both the gauge and the matter spins. So the spin flip is really generated by the sigma x. So that operation is also contained in the Hamiltonian. Okay.
I have a naive question. So, is it so you restricted R to be diagonal, and then is it the reason that why I got the Z2 spin liquid instead of a bigger like permutation gauge theory?
Oh, that part is actually it's related, but yeah, it's actually in the second slice. So the thing that because remember, I require the W matrix to be invariant under the L and R, right? So it means that once I specify my R matrix, for example, let's say I want to flip sigma 1 and sigma 2. So the R matrix is basically -1, -1, and +1, +1. I leave these two invariant. But the thing is that once I specify my my R matrix, L is no longer free because I solved this equation because that was my requirement. So L is uniquely determined by R. So you can see that these two things are slaved. So really, the symmetry is just Z2. You cannot freely permute anything on the matter spins. Yeah.
So can I ask one question?
Mm-hmm.
So the constraint on R to be diagonal, you put it by hand or it's from the system of the Hamiltonian?
I would say it's both, because the thing is, if you permute this Hamilton you know, if you permute the gauge spins on the lattice, I really don't know how should I interpret this thing.
So before you introduce this lattice description, just by looking at the Hamiltonian, then it's given by hand or it's automatic?
No, it's not really given by hand because the thing so far I've been saying that the R and the L matrices leave each star in there. Okay. Right. But the thing is, you know, eventually I have to put this thing on the lattice. But the thing is, when you put the thing on the lattice, I cannot just flip a single star because I have to make sure that the other stars are happy. And that basically requires that this is basically the symmetry of the Hamiltonian. It's the true.
So symmetry. Basically, you are requiring locality of the symmetry.
Exactly.
Okay. Thank you.
Okay.
Can I ask a naive question related to Hitcher's question? Do you have a non-local symmetries which allows the flipping or the spins in the space? Maybe you can ignore this and then you can answer maybe in the end if you have time. Maybe too naive. Sorry.
No, not too naive. But the short answer is I don't know, because I'm not sure whether it's whether that would involve some sort of because that probably you would probably operate on everybody, right? It's probably some sort of global symmetry. It's because on the lattice it's going to be a cascade.
That's
right?
Right. Okay. Thanks.
Yeah. Okay. Basically, let me just pause on this one again. So basically here I gave a concrete example of the R and L matrix so that it's clear, so that it's not so abstract. So suppose you know, I want to flip these two. I have the R matrix of this form, and then once I specify the R matrix, I solve for the L matrix, meaning that you know, the operations on the mu spins or on the matter spins are kind of slaved by the R matrix. And the spin, and as I said, the spin flips, there are such terms in the Hamiltonian because we have the transverse U. The spin flips in the Z is basically generated by the sigma X, but these terms are available in the Hamiltonian. So basically, yeah, you can do that. And the permutation, as I said, the permutation is really not physical. Here, it just corresponds to which one do I call a 1, 2, 3, and 4 of the mu spins. I mean, that's just my choice, right? So that's not a physical operation that's in the Hamiltonian. So this is also fine.
Can I ask you one more question?
Mm-hmm.
So are you using different R and L matrices for each side, or?
I will get to this question here.
Okay, thank you.
So it's really, they're all timely questions. So if you remember, so this transformation, the L and R, basically it leaves a single star invariant. However, now I have to, so on the lattice, I have to require Z2 gauge symmetry on the lattice. However, on the lattice, I cannot just take care of a single star. For example, I flip this spin here, I flip this spin here. I mean, within associate R and L matrix, I can heal this star. But if you look at these two stars, I have only flipped one gauge spin. So these stars, there is no way that I can that I can make these two stars happy just by monomial transformations, right? So on the lattice, similar to the Z2 gauge symmetry, where I cannot just flip, I cannot just apply sigma x's on these two links associated with a single star. I have to flip the minimal thing that I have to do here. I have to flip around an elementary plaquette. So basically, this is the local Z2 gauge transformation. And it's generated by this complicated operation. It's actually not that complicated. So here, I didn't write the R, but I write sigma x directly because you know that, I mean, in this language, the R is basically the sigma x on the flip spins, right? And so basically, you can see that for a plaquette, what I want to do is I want to flip the 4 gauge spins, 1, 2, 3, and 4. And once I specify that, this is equivalent to specifying the R for this star, the R for this star, and the R for this star and that star. And correspondingly, I can solve for the L that I have to do on the matter spins. So basically, it's really some sort of it's really, you're actually promoting the usual Z2 gauge symmetry, where you simply operate on the gauge spins, but now you have to do something on the matter spins as well. And but that operation on the matter spins is slaved by the spin flips on the gauge spins. So the symmetry is still Z2, and it's not some bigger symmetry group. And then you can show that this operator, this local gauge transformation that we constructed using this monomial transformations, it commutes with the Hamiltonian because, as I said, the spin flips are basically generated by sigma x and mu x. We have that terms in the Hamiltonian, and that operation leaves each star invariant. So I heal the 4 star after I do this. And also the permutation is not physical, it just corresponds to relabeling. So that's fine. So that commutes with the Hamiltonian. And this is true for arbitrary plaquette. So this is a local symmetry of the Hamiltonian. And because that involves spin flips, this is called combinatorial gauge symmetry. And also, this is the symmetry on the elementary plaquette. And then you can, of course, you can construct larger loops, for example, like this. Still, I mean, you specify which gauge spins that you want to flip along the loop, and then you can figure out the corresponding R transformation associated with each plaquette that you visit along the loop, and that will uniquely determine the L transformation that you have to do on each star. And let me emphasize that this symmetry is an exact local gauge symmetry for all values of the couplings. It doesn't require some sort of perturbation in the energy scales. Remember, we have this J and we have this gamma and gamma tilde. So far, I haven't really done any perturbation in these energy scales. So this is really an exact gauge symmetry that holds for arbitrary values of the coupling. Okay, I think before I continue, let me pause here. Is there any question so far?
Yeah, I have a question. So even though you have exact gauge symmetries, is the Hamiltonian exactly solvable too, or no?
No, this is not exactly solvable.
Hamiltonian is not exactly solvable.
It's not
Okay.
exactly solvable, but I will discuss, this is what I will talk about. I will discuss a particular limit where this Hamiltonian maps to the exactly solvable limit. Yeah.
Okay. But yeah.
Can I ask one more question?
Mm-hmm.
So again, it is based on that the monomial matrices. So like those generalized permutation operator, will it form a group again? It seems to me like it'll form some algebra. But I mean, it might close into an algebra, but not.
You're talking about which group?
I mean, the monomial. I mean, so you're saying you take the permutation matrices and and then change the entries to be elements of SU2 or something.
Mm-hmm.
So isn't that right? So you're changing the elements of the permutation group. I mean, the elements of each element of the permutation group into an SU2 element or something. So then will it still form a group?
Yeah, that I never deny. It is a group, but it's not S4. It's not permutation. Yeah, as I said, this group is actually a semi-direct product of two groups. Yeah.
Oh, so it is still a group, you say? Okay,
it's still a group. Yeah, it's a semi-direct product of the diagonal because the diagonal is a normal subgroup. Because if the diagonal matrix, I mean, you can act on that with permutation. It still is diagonal. So it's really yeah.
Okay. Okay.
I probably should have written that, but I never thought that somebody would ask it. But yeah, sorry. Yeah, that forms a group. Yeah.
I see. Okay. Okay. Thanks.
Okay. So, okay. Now I have discussed this this exact Z2 gauge symmetry, but still this model so far it looks not very familiar. It looks a bit maybe it's hard to digest everything. But now let me map this model to the familiar Z2 gauge theory, and in particular the one that I showed at the beginning in the special limit. Okay, but still, I mean, this is just to show that it boils down to that in the special limit, but it doesn't mean that the Z2 gauge symmetry relies on that. Okay. Now let me isolate a single star first. Okay, for the moment, let me turn off the transverse field, the gamma tilde I had on the gauge spins. So this is the term, this energy the Hamiltonian that I copied associated with a single star, with the ZZ coupling, the Ising coupling, and a transverse field on the matter spins. Okay. Now remember, I said there is no sigma and mu mu couplings. If you stare at this Hamiltonian, you will realize that for each mu spins, this Hamiltonian is nothing but a single spin in the tilted magnetic field. It's magnetic field at the z direction is given by this, and the x direction is the gamma, right? So you can actually diagonalize for each mu a independently, and then the Hamiltonian is basically a sum of all the EAs. And then that the eigenenergy associated with each mu a, they're independent. It's basically this squares plus this squared, and then you take the square root. And then of course you have a plus and minus sign, so you're not losing any degrees of freedom. You have a mu, and then here you still have the plus and minus sign. So this is the eigenenergy associated when you diagonalize for each mu a. And then you have a plus and minus sign. But now we're interested in a ground state. So it means that we have to choose minus sign for all, the A goes from 1/4. And then if you look at this part, this eigenenergy, this is a square root I can expand in Taylor series. Now for concreteness, let's just take, gamma to be bigger than J, and then this expansion is exact. And notice that the sigmas, basically here, they are just classical variables. Sigma squares to identity. So when you expand in series, actually this series actually terminates in terms of the Pauli operators, because sigma squares to the identity. So you can expand this in power series. You get some constant term, and then you get some quadratic term in the sigma I and sigma j z. And then you get some quartic terms. This is the only quartic term that you can generate. This is 1, because you only have 4 gauge spins, 1, 2, 3, and 4. Okay. Now, for low energy effective Hamiltonian, I choose the minus sign here for all the 4 gauge spin, matter spins, and I sum over A equal from 1 to 4. Okay. Now, if you look at this effective Hamiltonian, when you sum over A, recall that the Hadamard matrix has this property. A W transpose W is proportional to identity. And then if you look at this part, when you further sum over A, this part, the quadratic term, is nothing but W transpose W. And then this is proportional to delta Ij. So you see that the quadratic term that tends to give you some sort of ferromagnetic or antiferromagnetic ordering, it drops out precisely. So the only non-vanishing term here is basically the quadratic term, the quartic term. So you're left with an effective Hamiltonian in the low energy that has this form, a gamma minus lambda. Although I'm doing an expansion, but this expansion actually, this is exact. This expansion actually converges. So this is your Hamiltonian in the ground state sector. Ground state sector meaning that here, remember, I chose minus for all the stars. So this, if you look at this, this is basically the familiar term from the Z2 gauge theory. And this is really coming from the symmetry of the Hadamard matrix and also the symmetry, the underlying Z2 gauge symmetry. Okay. And now I can turn back on this transverse field on the sigmas, and then I get precisely the familiar form of Z2, that is gauge theory, in the low energy sector. Of course, I've chosen minus for all the sectors, but I can consider and further consider, I mean, so far everything is exact, but I can consider an asymptotic limit where I can make this, I can project precisely all the high energy sectors. This limit goes as follows. Now, suppose if you look at this term, an excited sector corresponds to if I choose plus instead of minus, right? So remember, I take gamma to be bigger than J. So the energy cost associated with flipping a sector is of the order of gamma. So I can consider I take gamma to infinity, meaning that I send all these high energy sectors to infinity. But at the meantime, I want this energy scale in front of this effective star term to be of order 1 because I don't want to kill that as well. But lambda you can express in terms of J over gamma. It takes this form. So basically, the asymptotic limit is I take gamma to infinity while keeping lambda of order 1 because I want this. This is the excitation, the energy cost of a star excitation within the toric hole or the Z2 gauge theory sector. Okay, I want to fix gamma to be of order 1, meaning that effectively I have to take J to go as gamma over 3/4. Gamma to the power of 3/4. So basically, in this limit, we have an exact Z2 gauge theory in the familiar form of this Hamiltonian. Okay. Is everything clear so far? Okay. So this is basically this model, and then how this maps to this familiar Z2 gauge theory. And here, there is some ongoing work. Let me just briefly mention about this model. Because I mean, this model, not this one, but the original Hamiltonian, it only contains 2 body interactions. So we can actually do quantum Monte Carlo study on this model. So basically, this is ongoing work by Kai-Xing Wu at Boston University. So from quantum Monte Carlo results, you can actually see that there is indeed a transformation, a phase transition from the Z2 quantum spin liquid to a confined phase. Once you fix, here gamma G is basically the gamma tilde, is a transverse field on the gauge spins. So basically, if you take a horizontal cut, so basically you have a phase transition similar to that in the Z2 gauge theory. So this is something, hopefully it will appear soon. Some numerical study. Okay, I think okay, I'm actually doing quite good in time. Let me mention that I can further construct a model because previously, remember, the starting point is really I construct exactly a star operator, right, with the Z2 gauge symmetry, and then I put the transverse field on the gauge spins. But if I put an additional set of auxiliary degrees of freedoms associated with each plaquette, and then I design a different coupling, like the similar coupling, but now in the x direction, I can construct precisely the plaquette operator as well. So now, for example, I can on top of this mu degrees of freedom, I can further introduce 4 let's just call tau spins associated with each elementary plaquette, and then I couple them with the Hadamard matrix. And now this term precisely corresponds to the plaquette operator. So now this Hamiltonian in the low energy sector would be exactly solvable. That's the one that corresponds to the Tarry-Codd Hamiltonian. And similarly, you have the combinatorial gauge symmetry associated with flipping around a star, and then that commutes with the Hamiltonian, also commutes with the plaquette operator as well. Okay, let me actually talk about a generalization.
Jicheng?
Mm-hmm.
Can I ask one question before you go to the 3D? So in your 2D models, I understand that in certain limits you can realize the Z2 spin liquid similar to the Tarry-Codd.
Mm-hmm.
But can you access other spin liquids like with the metallic matter fields or something like that? Or
yeah, this is part of the ongoing work. Like we are, I mean, of course we haven't really got to the non-abelian. I mean, this is going to be complicated, but
sure,
we are doing something that generalizes this thing to, for example, the Z3 model. This is the next non-trivial thing that you can do.
Oh, maybe my question is simpler. So the Tarry-Codd, the matter fields is gapped, right? But the in the like something like K-type model, you sometimes have a like Marana fermions and something like that, which is massless though. So in your Hamiltonian, it's not exactly solvable. So I'm not I don't see how many like different types of spin liquid you can realize in your model. Is there only a single Z2 spin liquid phase, or there are more than that?
Yeah, this is a good question. Yeah, maybe there are more if you, especially if you consider other type of matter field. For example, the matter field are not just for example, this kind of spin 1/2 objects, right? But
oh, I see. So what you're saying is, if I restrict the matter to the spins, then there is only one spin liquid.
Yeah, there are actually several things. So it has to do with the underlying, I mean, here these are spin 1/2. So I mean, it realizes Z2 gauge groups, and also you can. There are several ways of generalizing this. You can generalize. You can promote these two, for example, in other type of operators. For example, instead of spin, you can actually consider like Zn variables. That's one possibility, and the other possibility is to generalize the Hadamard matrix. Consider different form of Hadamard matrix, because I think for this particular form of Hadamard matrix, because the transformation is basically, the moment that we choose a transformation to be like -1s on the diagonal, it's like a Z2 operation, right? So maybe well, I mean, we hope that maybe one can play with the form of the Hadamard matrix, and we realize other type of spin liquids. But that would be the hope, right?
Okay. Yeah. Thank you very much.
No problem. Right. I think I'm getting towards the end. I mean, there's just a few more slides. So now, if you think about what we have done, basically we have a prescription of generating this the star operator that involves 4 spin operators. Okay. Then of course we can for all these models that involve 4 spin interactions, we can now realize. For example, in the 3D Tarry-Codd, of course, the star operator is a 6-body interaction. But on the other hand, the plaquette operator in the 3D Tarry-Codd is a 4-body interaction. So now we can start by engineering, instead of the star, we can start by engineering the plaquette operators in the same way. And then the transverse field is going to generate perturbatively. It's going to generate this star operator in the same way. I don't have to go in detail because you already know how it goes. And maybe the second, it's a trivial generalization, but the model is not so trivial. It's the so-called X cube model. And then the interesting thing is that it realizes a more exotic type of topological order, like the Fracton topological order. Right now, maybe I cannot even keep up with all these theoretical work on fractons, but if you ask about the experimental realizations, maybe I think I can still safely say that it remains elusive. I think I had this sentence like 1 year ago, but I think it still applies today. And there are proposals, of course, on realizing fractons using interacting Majoranas, but you can ask, is it harder to realize Majorana or is it harder to realize fractons? It's not right. So now we can actually using this prescription to realize a particular type of maybe it's the simplest type of fracton, the so-called X cube model. So in some sense, it's very similar to the 3D Tari code. But now the vertex operator, the star operator, is no longer a 4-body interaction. But then you have 3 different types of vertex operators associated with the x, y, and y, z, and the xz planes. And then the cube operators is a 12-body operator. Okay. Now, since here, I mean, again, we see this this familiar 4-body interaction, we can actually realize, by putting 12 mu spins associated with each group. Sorry, 4 with each group, and then we have 12 in total, and then we can actually realize this model. And by realizing, I mean, once you can write down this model in terms of simple, 2-body interactions, these are physical interactions that you can program in various experimental platforms. And in particular, it's simple that in the sense that there is only a ZZ interaction and transverse field term. And the nice thing is about this is really the minimal quantum mechanical model that you can have. Like, for example, in these quantum annealers, like D-wave machines, they can basically program ZZ interaction and the transverse field, because of course, I mean, when you write down a certain model with 2-body interaction, like the Kitaev honeycomb model, of course, this is also 2-body interaction, but then it's highly anisotropic. To realize that model, you would need all the XX and YY and ZZ. So if there is a hardware that can already give you the XX and YY and all the ZZ simultaneously with no caveats, then I would say you can use that. You can do quantum simulations on all these interesting the Heisenberg model on whatever lattice you get, but we don't have that yet. So it's really, I mean, but using this construction, you really need the simplest type of interaction that you can realize. Okay, this is my second to last slides. Let me just briefly mention, this is a new progress. This is a work by Claudio Chamon and Dimitri Green that appeared on the archive in June, and this is the paper. If you're interested, I suggest that you take a look. So basically, they construct the same sort of the Z2 spin liquid, but they replace the spins, degrees of freedom, with superconducting wires. And to be more precise, the phases of the superconducting wire. And for example, you can see that this is each. They put this in this kind of waffle geometry, and each waffle is essentially a star. And then you have 4 sort of gauge wires with the phase labeled by theta, and then 4 matter wires with the phase labeled by phi. And now the spin couplings here are replaced by the so-called Josephson couplings, right? So the Josephson coupling are still encoded by this Hadamard transformation, sorry, the Hadamard matrix. And now, in terms of this superconducting wires, the quantum mechanical term, sort of the analog of the transverse field, here is just the capacitance term. And then you can see that here, well, a spin flip in this language now becomes a pi phase shift of the superconducting wire that can be generated by the capacitance term because they are conjugate variables. And this model is very interesting. It has an interesting phase diagram. It's actually, because now you see that these phi and theta, they are continuously, like they're U1 continuous variables. So it turns out that this model at 0 temperature, it it has this interesting feature of an XY disorder, but with Z2 topological order on top of that. Here I only have one slide. I only want to point you to this paper if you're interested in more details. Okay, so let me put back this summary of our main results, and thanks for your attention.
Can I ask you something?
Mm-hmm.
Yes. Okay, so you discussed all the abelian cases, and you say that you can also try and generalize to like Zn. So do you think you would also be able to find like all the other quantum double models of Kitaev? Like you will get a two-body Hamiltonian?
Well, that's why that would be the optimal scenario. But as I said, we haven't tried. We haven't really thought about the non-abelian case yet. So yeah, if you're asking about the all the other, especially the non-abelian models of the quantum double, then I don't know. Yeah, but the Z3, I think we have a Z3, of course. I mean, also the ZNs, I think we have a shot. Mm-hmm.
So how do you introduce orientation in your picture? So is it the same? You just put an orientation on every edge?
Yeah. I mean, of course, you cannot use spins, right? You have to use something else that plays the roles of a sort of a clock operator. But for example, you can use superconducting wires. Yeah.
Okay, I think you're
because for spins, you know, you can really go between plus and minus one. But for some other degrees of freedom, like phases, right? And then you can sort of you can if you can achieve you can make it in such a way that the classical minimum is is sort of is discrete, then and it's not just two variables, then you can achieve that.
Okay, thanks.
Mm-hmm.
Okay. Is there any other questions, comments? So I have a question. So do you think the superconducting circuit is probably the easier to realize the spin liquid you wrote down in your paper, or
yeah,
than other schemes? Yeah.
I think this is certainly very this is actually a promising candidate. But actually, at the beginning, what we had in mind is basically this quantum annealer, like D-wave machines that people have for quantum computing. Because the thing is really quantum annealers. Because now you see that well, quantum annealing, people are kind of not as optimistic as back in the days about the computational power of like adiabatic algorithm, like quantum annealing, in terms of quantum annealers. So is that annealer really that useful? I mean, because it's so restrictive in the sense that it only has ZZ and the transfer suit interaction.
Yeah.
But what we are doing here is that this construction, it can be programmed in this D-wave, for example, D-wave architecture, that you can actually encode this type of 6 and 8 vertex models on that. And actually, we have precise mapping that I think maybe in the latest version it's gone of the paper, it's gone, but we actually have that somewhere. Yeah, so I think that part is also maybe promising. But then the question is, of course, how quantum mechanical are these D-wave machines? But that's another question. Yeah.
Okay, I will look into your previous version of archive file. Yeah.
Yeah.
Is there any other question or comment? Okay. If not, then the time is up. So let's thank the speaker again. And yeah, the session is over. But before finishing up, I would like to remind you that if you didn't register to the website, so I put the link to the registration. So if you didn't do that yet,